For the past several months, I've worked with Dr. Wang and her team of researchers aiding in the collection of images using a drone. And I've noticed a few issues: the safety of current methods, the high cost of gathering aerial data, and the low quantity of data collected due to the high cost. The most pressing issue is the lack of safety equipment and procedures currently being utilized to collect aerial images. The Hancock Agricultural Research Facility is located in close proximity to several private growing operations. These private growers routinely utilize manned aircraft to apply chemical agents to their fields, and I have observed these aircraft fly over Hancock well under 400 feet, bringing them within the area of every research group's drone operations. This poses a problem for all researchers who utilize drones, because the FAA requires that drones yield to manned aircraft at all times. Meaning, if a collision were to occur, the drone pilot, research group, and potentially the university as a whole could face substantial legal consequences. But let's put a pin in that and talk dollars and cents. Operating a drone program is expensive and time-consuming. From sending researchers to Hancock, maintaining equipment, and coordinating flights around the necessary field operations, a lot of valuable time is wasted. In addition to wasted time, the equipment and software comes at a high cost. So to remain within budgetary constraints, sacrifices in hardware or software are usually necessary, limiting the quality of data that can be collected. For aerial images to be collected, a person must be A, physically on site, and B, maintain visual contact with the drone while it completes a pre-planned flight mission. And as a result of the high travel costs for researchers to be physically present, the frequency of data collection is limited. This poses a problem for what many of you are working towards: developing a machine learning model capable of correlating RGB or multispectral images with crop health. Without access to large quantities of images at a low cost, the development and deployment of these models is made all the more challenging. But last year, something kind of exciting happened. Enter the DJI Dock, a completely autonomous UAV system designed to eliminate the need for a person to be physically present for aerial images to be collected. The dock is installed at the desired location and allows the drone to take off, perform its pre-planned flight mission, and land autonomously, while also taking care of required battery maintenance without human intervention. Images taken by the drone are then wirelessly uploaded to a cloud platform where they can be accessed in their raw form or distributed to a third party for analysis. This last step in autonomy eliminates the need for a person to be physically present in order to collect aerial images, which will save hundreds of hours, thousands of dollars in labor costs, and allow researchers to focus entirely on what matters. Another benefit to the increased autonomy that the dock allows is the ability to collect aerial images around the clock. The aircraft can remain airborne for 35 plus minutes in a single flight and can be charged fully in less than 30 minutes, meaning aerial images can be collected on a daily or even hourly basis. This exponential increase in data quantity allows for a more comprehensive understanding of the correlation between images and the real status of crops, speeding up the development of machine learning models and allowing for automatic monitoring and analysis once a model has been fully deployed. The final monetary benefit to the DJI Dock is the ability to split the cost of operating a drone program among many research teams. The more teams we have on board, the lower the cost becomes, and the more resources we have to invest in the best imaging technology available. Finally, and most importantly, this program is designed to prevent a collision between a manned aircraft and a drone. There are two ways we're going to go about this: information in and information out. Information out involves simplifying the lines of communications for all research groups. Instead of coordinating flights with private companies, federal agencies, and state agencies, all research groups would be able to submit their desired flight schedule to one easy-to-reach point of contact. This point of contact will then handle broadcasting the master flight plan so that manned aircraft have a better understanding of where we are and when, significantly reducing the risk that manned aircraft will enter our airspace, and therefore a collision. However, while vital, information out only discourages manned aircraft from entering the flight paths of our drones. Because we conduct drone flights in what's called uncontrolled airspace, it's up to us as drone pilots to know where manned aircraft are at all times and to reliably avoid them. This is where information in comes into play. Information in consists of two technologies, radar and ADS-B. ADS-B is used by most manned aircraft to broadcast their exact location, speed, and direction of travel, allowing a drone to sense and avoid a collision hazard in real time. The problem we face is that most manned aircraft that perform chemical application services, otherwise known as crop dusters, are not equipped with ADS-B transponders, making detection and avoidance difficult. The solution to a lack of data emitted by the manned aircraft is omnidirectional radar. By integrating an omnidirectional radar into the unmanned flight system of the dock, the drone can be alerted when a manned aircraft enters its airspace and autonomously avoid its flight path, eliminating the risk of a collision. The program I'm proposing involves quite a few moving parts, and is admittedly ambitious. It will require time and resources to get off the ground. However, I believe the benefits far outweigh the costs. The use of drones in research and the private sector has exploded over the past few years and is only projected to increase. With the increased volume of unmanned aircraft in our skies, it is paramount to our success to ensure that a collision between an unmanned and manned aircraft does not happen.